So clustering organizes the instances into meaningful subgroups or clusters without having any prior knowledge of their group memberships. Okay. Each cluster defines a group of objects that share a certain degree of similarity, but are not more dissimilar to objects in other clusters. Okay, that's a very formal definition of what clustering is. You can pause the video and digest that. I tried to explain it in more layman terms in the previous slide, but that's essentially what clustering is. And so, like I said, you don't know what meaningful subgroups might exist within that data, so you can't pre-label any data set. So you essentially have to give your algorithm an unlabeled data set, thus making this an unsupervised learning problem. A great technique for structuring information and deriving meaningful relationships for data. So clustering is a great technique for structuring information and deriving meaningful relationships from data. So you can often find relationships or insight into your data that is not often very clearly visible from just observing or exploring the data using traditional means. You can do that using clustering. This is an example that I mentioned. It can allow marketers to discover customer groups based on their interests in order to develop distinct marketing programs. This is the same example that I mentioned to you previously. Dimensionality reduction. Often data can have a high dimension, a large number of features. The goal is to simplify the data by reducing the number of dimensions without losing too much information. One way is to merge several correlated features into one. So for example, a car's mileage may be highly correlated with its age. So they may be merged into one feature that represents the car's wear and tear. So that's a very good example of dimensional reduction. That's something that you might probably do yourself when you're pre-processing your data, and you might play around with your data and do this on your own before feeding it into a machine learning algorithm. But sometimes you have data that has way too many variables, and many of these variables are not very intuitively understandable, in the sense that like a car's mileage or its age might be easy to grasp. So it might be very hard for you to come up with ways to collapse certain columns into single columns, and so you have to use machine learning algorithms to do this. It can improve the computational and sometimes the predictive performance of machine learning algorithms, and it reduces storage requirements, right? So because you're storing less variables and thus less data. And anomaly detection. The system is trained with normal instances, and when it sees a new instance, it can tell whether it looks like a normal one or it is likely an anomaly. So, that's essentially how an anomaly detection algorithm works. You give it non-anomalous instances, and so it gets acquainted with those instances, it gets acquainted with what normal instances look like, and when something that doesn't fit that impression comes along, it detects it as an anomaly. An example would be detecting unusual credit card transactions to prevent fraud. Okay, so that would mean you have to supply it with a bunch of normal credit card transaction data, and obviously this data is not labeled because all of it is normal. So if you wanted to label it, you can just say all of them, you can label them all as normal, which, doesn't make sense because they're all the same. Anyway, so it's basically unlabeled data. So unusual credit card transaction data. And so after being trained on this data, if a new transaction happens that doesn't seem to fit the data you trained the model on, it detects it as an anomaly. So this is a good example of why in machine learning, the more data you have, the better. So the model can get a better sense of what it's expected to look for and that kind of stuff. Another example would be catching manufacturing defects or automatically removing outliers from a data set before feeding it to another learning algorithm. Again, there are many, many examples. Any one of these, if you want to learn more about it, just go into Google. There are a lot of resources, a lot of threads. A lot of people have asked questions like, what is supervised learning or how anomaly detection works, or, anything of that sort. So you can go and you can explore, and you should get used to looking stuff up like this on your own. In order to be a good data scientist, you need to know how to research and to learn. And finally, reinforcement learning. We're not going to go too deep into this because, again, this is not a very common type of learning that's taught. Most courses that teach reinforcement learning teach just reinforcement learning. They focus on just that because the set of problems that it solves are unique compared to the problems we're trying to solve, which can be a wide variety of different types of actual, business problems. So the goal in reinforcement learning is to develop a system, or often called an agent, that improves its performance based on interactions with the environment. So the agent observes the environment, selects and performs actions, and gets rewards or penalties in return for those actions. And it learns the best strategy, or, in reinforcement learning, we call it policy, to get the most rewards over time. So, an example of reinforcement learning is like learning to play a game, right? So your system or agent would try different methods of playing the game, and each method would, or each set of or sequence of actions, let's say, for playing that game would result in a different score. Some of them would have result in a higher score, some of them would result in a lower score. And so if you reward those sequences of actions that result in a higher score more compared to other sequences of actions, then eventually over time it'll learn to start using actions in its sequences that further increase the rewards it's getting, and eventually it will learn how to play that game or solve that problem or whatever it may be you're trying to do. So that's reinforcement learning. Again, we're not going to really go into it. So let's summarize the different approaches, machine learning approaches that we learned about. So we said that we have supervised learning, unsupervised learning, and reinforcement learning. The main difference between supervised learning and unsupervised learning is that supervised learning trains on labeled data, whereas unsupervised learning trains on unlabeled data that has no labels, no known outcomes. And in supervised learning, direct feedback is given, whereas in unsupervised learning, there is no feedback. And supervised learning is generally used to predict an outcome or to predict the future, whereas unsupervised learning is used to find hidden structure in data most often. And reinforcement learning, it's its own approach. It has a reward system and learns series or sequences of actions and so on and so forth. So it's its own beast that we're not going to really go into, but you should know the difference between supervised learning and unsupervised learning. If you only take that away from this introduction section, that's enough, right? Know the difference between supervised learning, unsupervised learning, know how to recognize a problem as a supervised learning problem or an unsupervised learning problem, and learn to recognize the different unsupervised learning approaches as regression and classification. That's really all you need to have learned from this section. Now let's talk about a concept in machine learning called generalization. So generalization is the ability of a model to perform well on new data. So basically the ultimate objective of machine learning, we're using training data, we're using historic data to train the model, but the whole aim of even training a model, of creating a model, is so we can predict on new data, right? So the better it performs on new data, the better the model, the better we've achieved our goal. So it's very important for you to follow certain principles that will allow you to build a model that can train better on new data. And the better the model performs on new data, the more general you can say it is, and the more you can trust that it will give you what you're looking for. So how do you tell if a machine learning model is generalizing well? So this is a very important topic, and you have to drill into your head that the importance of a testing set. Okay, so in order to tell if your machine learning model is generalizing well, you have to split data into two sets: the training set for training the model, and the testing set for evaluating the generalization performance of the model. So you have to do this before you do anything. You split your existing data into a training set. Often 70% of your existing instances, labeled instances, are used for the training set, and you withhold the other 30% or however many percent you chose to withhold as a testing set. Now this testing set will be used to evaluate or verify the performance of your model. If you don't do this, you can never know if your model will predict accurately on new data, because you've spent all your existing data training the model. So the model knows your data very well and might not generalize well. So it's very important that you withhold a certain percentage of your data, your initial data, as a testing data set, and you evaluate the performance of your model after you've trained it on that data set. And based on that result, you can know how well your model does in terms of generalization. Now, some difficulties of machine learning include bad data and bad models. So machine learning means training a model on data, right? That's basically the definition of machine learning. So there are two things that can go wrong. You can have bad data, which will result in a bad result, or your model can be bad. What do we mean by bad data? So there are some data challenges that we should be aware of. For example, you might have the quality of your data, of your training data, might be low. So especially for hard problems like image and speech recognition, you really need to make sure that you have a lot of data and that this data is accurate and that it's varied enough that your model can really develop a very good recognition system. Some challenges you might face when it comes to the data side of machine learning is insufficient quantity of training data. So especially when it comes to very complex or high level problems like image and speech recognition, the more data you have, the better. We already established that fact, but sometimes for complex problems, you really need to have a lot of data. It's not just that the more you have, the better it'll be. It's that you need to have a lot of data for it to work. Otherwise, it's not going to work. So many projects are hindered by insufficient quantity of training data. When it comes to image and speech recognition, in the worst case, you can allocate resources and you can go have people like label data and that kind of stuff. But in other cases, you might not physically have that data, right? If you want to build a system for detecting or, for predicting loan success rates or something, you might just not have access to existing data on defaulted loans. Your data might be insufficient in terms of, its quantity. And this is a very real problem that you might face. So that's one of the first things you should make sure of before taking on a machine learning project. Make sure that you can access enough data if needed. Another problem that you might face or challenge would be non-representative training data. So in order to generalize well, it is crucial that your training data is representative of the new cases. So if you give your model a bunch of cases that have nothing to do with, or a bunch of labeled instances or cases that have nothing to do with what you wanted to predict in the future, that's not going to really benefit you at all. That's not going to train a model for. You need to find data that's very representative of those exact cases or instances that you're expecting to predict using your model. Another problem is poor quality data. So training data full of errors or outliers and noise. So noise can come from a variety of reasons. It can be human error. It can be due to, insufficient quality of tools used to measure the data, so on and so forth. But all of this makes it harder to detect the underlying patterns because these errors cover up the pattern, if you will. So missing data is also a problem, right? So making it less likely that the model will perform well. Often well worth the effort to spend time cleaning up the trained data. That's very true. The more time you take to actually clean up the data and make the data or increase the quality of the data by spending time on it, pre-processing, etc., the better the chance that your model will be able to find an accurate relationship between the input and the output. And so, that you'll be able to use it effectively. And that's actually what, it's a running joke, that data scientists spend 80% of their time cleaning up data. And that's very true because, you're never going to get 100% best quality data. There's always going to be some problems in the data, and you're going to have to go in and figure out how to make it better for your model.